studied section 13, Natural Deduction. Introduction. In this study section, we will explore the method of natural deduction. This method consists of the deduction of the conclusion of an argument from the premises by using certain basic argument forms already known to be valid. We shall therefore learn how to construct formal proof of validity for arguments using the rules of inference and the rule of replacement. Learning outcomes. When you have studied this section, you should be able to construct a formal proof of validity for arguments using the rules of inference and the rule of replacement. The method of deduction. The method of deduction as a technique for analyzing arguments is different from the truth table method in some significant ways. First, this method is informed by a principle which states that if an argument is valid, then its conclusion must follow from its premise or premises. The method is, therefore, meant to show or prove that the conclusion of an argument actually follows from its premises. The second point of difference follows from the first, and it is that the method of deduction, unlike the truth table method, is not a decision procedure. What this means is that whereas the truth table can be used to determine both the validity as well as invalidity of arguments, the method of deduction can only be used for valid arguments, and the task here is to show constructing a proof that the conclusion of the argument actually follows from its premises. In doing this, we construct a chain between the premises and conclusion using some basic argument forms as rules of inference and in some logical equivalencies as rule of replacement. These rules serve as links within the chain. It is an obvious fact that if an argument is valid, its conclusion must be derivable from its premises. But we must warn that there may be occasions when we are not able to derive the conclusion of an argument from its premises. This, however, does not mean that the argument in question is invalid. The problem may be due either to our own inability to provide a formal proof of validity for the argument or the fact that we are not sufficiently aware of all the relevant rules needed to construct the proof. Let us proceed by learning the rules of inference. Rules of inference. A rule of inference is a rule to the effect that it is logically permissible to assert a certain conclusion when certain premises are given. The valid argument forms discussed in Lecture 11 also serve as rules of inference when providing formal proof of validity for arguments. Let us now look at some of these rules. Number 1. Modus ponens, known as MP, also known as affirming the antecedent AA. P, then Q. P, therefore Q. Given a conditional statement and given the affirmation of its antecedent, it is permissible to affirm its consequent. Number 2. Modus tollens, MT, also known as deny the consequent, DC. P, then Q. Not Q, therefore not P. Given a conditional statement and given a negation or denial of its consequent, it is permissible to infer the negation of its antecedent. Number 3. Hypothetical syllogism, HX. P then Q. Q then R. Therefore, P then R. Given two conditional statements such that the consequent of one matches the antecedent of the other, it is permissible to infer a conditional having the unmatched antecedent and the unmatched consequent. Number 4. Disjunctive syllogism, DS. P or Q, not P, therefore Q, or P or Q, not Q, therefore P. Given a disjunction and given a denial or negation of any of the disjuncts, it is permissible to affirm the other disjunct. Number 5. Simplification, known as simp. P and Q, therefore P, or P and Q, therefore Q. Given a conjunction, it is permissible to infer any of the conjuncts. Number 6. Addition. P, therefore P or Q, or P, Q, therefore P or Q. Given a statement, it is permissible to infer a disjunction having that statement as one disjunction, or given two existing statements, it is permissible to form a disjunction of the two statements. Number 7. Conjunction. P, Q, therefore P and Q. Given two separate statements, it is permissible to conjoin both statements. Number 8. Constructive dilemma. CD. P, then Q, and R, then S. P or R, therefore Q or S. Given two conditional statements and a conjunction of these two conditionals, and given also the disjunction of their antecedent, it is permissible to infer the disjunction of their consequence. Number 9. Destructive dilemma, DD. P, then Q, and R, then S. Not Q or not S. Therefore, not P or not R. Given two conditional statements and a conjunction of these two conditionals, and given also the disjunction of their negated consequence, it is permissible to infer the disjunction of their negated antecedents. In applying the rules of inference, we should note two essential points. The first is that these rules apply to any argument containing statements having the form of these rules, however complex these arguments are. For example, the rule of modus ponens can be applied to the following arguments: A or B and C, then D or E. A or B, then C. Therefore, D or E. The second point is that we can only apply the rules of inference to complete statements and not to part of statements. For instance, the rule of modus ponens cannot be applied to the following argument for the reason that A is only part of a complete statement. A or B, then C. A, therefore C. Let us now identify the rule of inference by which the conclusion follows from the premise or premises in each of the following arguments. Number 1. A or B, then D. Not D, therefore not A or B. The answer is modus tollens, MT, also known as deny the consequence, DC. Number 2. A, then B, and C, then D. A or C, therefore B or D. The conclusion of this argument follows from its premises by rule of constructive dilemma, CD. D. Number 3. A, then B, if and only if not C. B, if and only if not C, then D. Therefore, A, then D. The conclusion of this argument follows from its premises by rule of hypothetical syllogism, HX. Number 4. A, then not B, and not C, then D. Therefore, A, then not B. The conclusion of this argument follows from its premise by rule of simplification. Number 5. A, then not B, and C, then D and E. Not B or not D and E. Therefore, not A or not C. The conclusion of this argument follows from its premises by rule of destructive dilemma, DD. Question. Mention the rules of inference you know. Feedback. We have 9 of them, and they are modus ponens, modus tollens, hypothetical syllogism, disjunctive syllogism, simplification, addition, constructive dilemma, disjunctive dilemma, and conjunction. Having now identified the rules by which the conclusions of some arguments follow from their premises, let us now construct a formal proof of validity for some arguments and then attempt to state justification for every line that is not part of the original premises. A and B, then I bracket open, A and B bracket closed, then parenthesis open, A, then brackets open, D and E bracket closed, parenthesis closed, bracket open, A and B bracket closed, and C. Therefore, D or V. 1. Bracket open, A and B bracket closed, then parenthesis open, A, then bracket open, D and E bracket close, parenthesis closed. 2. Bracket open, A and B bracket closed, and C slash therefore D or E. 3. A and B. 2. Simplification. I bracket open, A and B bracket closed, then parenthesis open, A, then bracket open, D and E brackets closed, parenthesis closed, bracket open, A and B bracket closed, and C. Therefore, D or E. Number 1. Bracket open, A and B bracket closed, then parenthesis open, A, then bracket open, D and E bracket closed, parenthesis closed. 2. Bracket open, A and B bracket closed, and C slash therefore D or E. Number 3. A and B. Number 4, A, then bracket open, D and E bracket closed. Number 5, A, number 6, D and E. Number 7, D, where number 2 is under simplification. Number 1 and 3 is under modus ponens. Number 3 is under simplification. Number 4 and 5 are under modus ponens. Number 6 is under simplification. Number 7 is under addition. Number 8, D or E. I. F or brackets open, G or H bracket closed. Bracket open, G, then I bracket closed, and bracket open, H, then J bracket closed. Bracket open, I or J bracket closed. Then bracket open, F or H bracket closed. Not F, therefore H. Number 1, F or bracket open, G or H bracket closed. Number 2, bracket open, G, then I bracket closed, and bracket open, H, then J bracket closed. Number 3, bracket open, I or J bracket closed, then bracket open, F or H bracket closed. Number 4, not F slash, therefore H. Number 5, G or H. Number 6, I or J. Number 7, F or H. Number 8, H, where number 1 and 4 fall under disjunctive syllogism. Number 2 and 5 fall under constructive dilemma. Number 3 and 6 fall under modus ponens. Number 7 and 4 fall under disjunctive syllogism. I. Bracket open, G, then H, bracket closed, then bracket open, I if and only if J, bracket closed. K or not, bracket open, L, then M, bracket closed. Bracket open, G, then H, bracket closed, or not K. N, then bracket open, L, then M, bracket closed. Not bracket open, I if and only if J, bracket closed. Therefore, not N. Number 1, bracket open, G, then H, bracket close, then bracket open, I if and only if J, bracket closed. 2, K or not, bracket open, L, then M, bracket closed. 3, bracket open, G, then H, bracket closed, or not K. 4, N, then bracket open, L, then M, bracket closed. Number 5, not bracket open I if and only if j bracket closed slash therefore not n. 6. Not bracket open g then h bracket closed. Number 7. Not k. Number 8. Not bracket open l then m bracket closed. Number 9. Not n, where 1 and 5 are under modus tollens. 3 and 6 fall under disjunctive syllogism. 2 and 7 also fall under disjunctive syllogism. 4 and 8 fall under modus tollens. IV. M then N. N then O. Bracket open. M then O. Bracket closed. Then bracket open. N then P. Bracket closed. Bracket open. M then P. Bracket closed. Then Q. Therefore, Q. Number 1. M then N. Number 2. N then O. Number 3. Bracket open. M then O. Bracket closed. Then bracket open. N then P. Bracket closed. Number 4. Bracket open. M then P. Bracket closed. Then Q slash therefore Q. 5. M then O. 6. N then P. 7. M then P. 8. Q, where 1 and 2 fall under hypothetical syllogism. 3 and 5 fall under modus ponens. 1 and 6 fall under hypothetical syllogism. 4 and 7 fall under modus ponens. V. Bracket open, not K and P bracket closed, then bracket open B or R bracket closed. Not K, then bracket open B, then D bracket closed. K or bracket open R, then E bracket closed. Not K and P, therefore D or E. Number 1. Bracket open, not K and P, bracket closed. Then bracket open B or R, bracket closed. Number 2. Not K, then bracket open B, then D, bracket closed. Number 3. K or brackets open R, then E bracket closed. Number 4. Not K and P slash therefore D or E. Number 5. Not K. Number 6. B, then D. Number 7. R, then E. Number 8. Bracket open B, then D bracket closed, and bracket open R, then E bracket closed. Number 9. B or R. Number 10. D or E. Where 4 falls under simplification. Number 2 and 5 fall under modus ponens. Number 3 and 5 fall under disjunctive syllogism. Number 6 and 7 fall under conjunctive. Number 1 and 4 fall under modus ponens. Number 8 and 9 fall under constructive dilemma. The rule of replacement. There are many valid arguments that cannot be so proved by using only the 9 rules of inference discussed thus far. Hence, the need for additional rules. The rule of replacement permits us to replace a whole expression or part of that expression with a different but logically equivalent expression. Rules of inference, therefore, the rule of replacement can be applied either to all lines or to parts of lines. The idea of the rule of replacement is that if two statements are logically equivalent, then they are either both true or false, thereby having the same logical force. The rule of replacement therefore authorizes specified logically equivalent expressions to replace each other wherever they occur, even where they do not constitute all lines of a proof. Below are the logical equivalencies that make up the rule of replacement. Number 1. De Morgan's theorems, abbreviated as DEM. Not bracket open P and Q bracket closed if and only if bracket open not P or not Q bracket closed. Not bracket open P or Q bracket closed if and only if bracket open not P and not Q bracket closed. Number 2. Commutation, COM. Bracket open P or Q bracket close if and only if bracket open Q or P bracket closed. Bracket open P and Q bracket closed if and only if bracket open Q and P bracket closed. Association, ASSOC. Parenthesis open P or bracket open Q or R bracket closed, parenthesis closed, if and only if parenthesis open bracket open P or Q bracket closed or R parenthesis closed. Parenthesis open P and bracket open Q and R bracket closed, parenthesis closed, if and only if parenthesis open bracket open P and Q bracket closed and R parenthesis closed. Number 4. Distribution, DIST. Parenthesis open P and brackets open Q or R bracket closed, parenthesis closed, if and only if parenthesis open bracket open P and Q bracket closed or bracket open P and R bracket closed, parenthesis closed. Parenthesis open bracket open P or Q bracket closed and bracket open P or Q or R bracket closed, parenthesis closed. Number 5. Double negation, known as DN. P if and only if not P. Number 4. distribution dist, parenthesis open P and bracket open Q or R bracket close parenthesis close if and only if parenthesis open bracket open P and Q bracket close or bracket open P and R bracket close parenthesis closed. Parenthesis open P or bracket open Q and R bracket close parenthesis close if and only if parenthesis open bracket open P or Q bracket closed and bracket open P or R bracket close parenthesis closed. Number 5. Double negation DN. P if and only if not P. Number 6. Transposition known as trans. P then Q if and only if not Q then not P. Number 7. Material implication MI. P then Q if and only if not P or Q. Number 8. Material equivalence ME. P if and only if Q if and only if parenthesis open bracket open P then Q bracket close and bracket open Q then P bracket close parenthesis closed. Bracket open P if and only if Q bracket closed if and only if parenthesis open bracket open P and Q bracket closed or bracket open not P and not Q bracket close parenthesis close. Number 9. Exportation EXP. Parenthesis open bracket open P and Q bracket closed parenthesis closed if and only if parenthesis open P then bracket open Q then R bracket closed parenthesis closed. Number 10. Tautology TAUT. P if and only if P or P. P if and only if P and P. Let us now identify the rule of replacement by which the conclusion follows from the premise or premises in each of the following arguments. Number 1. Bracket open, not A then B, bracket closed, and bracket open C or not D, bracket closed. Therefore, bracket open, not A, then B, bracket closed, and bracket open, not D or C, bracket closed. The conclusion of this argument follows from its premise by rule of commutation COM. 2. Bracket open, not E or F, bracket closed, and bracket open G or not H, bracket closed, bracket open E then F, bracket closed, and bracket open G or not H, bracket closed. The conclusion of this argument follows from its premise by rule of material implication MI. Number 3. Bracket open I then not J, bracket closed, or bracket open, not K, then not L, bracket closed, bracket open, I, then not J, bracket closed, or bracket open, L, then K, bracket closed. The conclusion of this argument follows from its premise by rule of transposition. Number 4. M, then not bracket open, N or not O, bracket closed. M, then not bracket open, not N, and not O, bracket closed. The conclusion of this argument follows from its premise by rule of De Morgan's theorems, DEM. Number 5. Bracket open, C and not D, bracket closed, then bracket open, E if and only if not F, bracket closed. Bracket open, C and not D, bracket closed, then parenthesis open, bracket open, E and not F, bracket closed, or bracket open, not E and not F, bracket closed, parenthesis closed. The conclusion of this argument follows from its premise by rule of material equivalence, ME. Question: what are the rules of replacement you know? Feedback: they are De Morgan's theorems, commutation, association, distribution, double negation, transposition, material implication, tautology, material equivalence, and transposition. Having now identified the rule of replacement by which the conclusion of some argument follow from their premise, let us now construct a formal proof of validity for some arguments and then attempt to state the justification for every line that was not part of the original premises by appealing to the 19 rules. Number 1. Bracket open, J, then L, bracket closed, then M. Number 2. Not K or N slash therefore K, then bracket open, M and N, bracket closed. 3. Bracket open, K and J, bracket closed, then L. Number 4. K, then bracket open, J, then L, bracket closed. Number 5. K, then M. Number 6. Not K or M. Number 7. Bracket open, not K or M, bracket closed, and bracket open, not K or N, bracket closed. Number 8. Not K or bracket open, M and N, bracket closed. Number 9. K, then bracket open, M and N, bracket closed. Where number 1 is under COM, number 4 is under EXP, number 5 and 2 are under HX, number 6 is under MI, number 7 and 3 are under CONG, number 8 is under DIST, and number 9 is under MI. Number 4. X then G. Not X then E. therefore G or E. 1. S then G. 2. Not S then E slash therefore G or E. 3. Not G then not S. 4. Not G then E. 5. Not G or E. 6. G or E, where number 1 is under TRANS. Number 2 and 3 are under HS. Number 4 is under MI. Number 5 is under DN. Number 5. S then bracket open T then U bracket closed. U then not U bracket open V then S bracket closed and bracket open W then T bracket closed. Therefore V then not W. 1. S then bracket open T then U bracket closed. Number 2. U then not U. Number 3. Bracket open V then S bracket closed and bracket open W then T bracket closed slash therefore V then not W. Number 4. Bracket open X and T bracket closed then U. Number 5. Not U or not U. Number 6. Not U. Number 7. Not bracket open S and T bracket closed. Number 8. Not X or not T. Number 9. Not V or not W. Number 10. V then not W. Where number 1 is under EXP. Number 2 is under MI. Number 5 is under TAUT. Number 4 and 6 are under MT. Number 7 is under DEM. Number 3 and 8 are under DD. Number 9 is under MI. Study section summary. In this study section, you learned that the method of natural deduction consists of the deduction of the conclusion of an argument from the premises by using some basic argument forms and logical equivalencies as rules. We constructed a chain between the premises and conclusion by using these rules, which serve as links within the chain. This method is employed only for valid arguments and is informed by a principle which states that if an argument is valid, then its conclusion must follow from its premise or premises. This is the end of section 13. Thank you for listening.